Back in the 18th century, when we had fur trappers all over North America, they would take some of their food and maybe some firewood and some supplies. They would take a little bit of that from their cabin and they would store it in little underground storage spots called a cache. So a cache was basically a little bit of what you already have put a lot closer to you. That way, if they're out in the woods or something and they run into trouble, they don't have to go all the way back to their cabin to get food or firewood or whatever they need. They can just go into a cache. Well, CPUs use cache all of the time. And in this episode, what I want to do is talk about the concept of caching, and I'm going to concentrate on what we call a CPU cache. So in order to understand how caches work, let's start talking about how programs move from your hard drive into the CPU. In other episodes, we talk about how when you start a program, so when you're double-clicking on an icon, the program, or at least some of the program, is copied off of the hard drive and placed into RAM. So some part of your RAM now stores that program. Now, once the program is in here, individual lines of the program are fed into the CPU via its external data bus, and the program is then processed. The problem we have is that CPUs are blindingly fast. RAM is fast, but not nearly as fast as a CPU, and then hard drives are fast, but not nearly as fast as RAM. So that creates a problem. There are points where the CPU needs the next line of code to be added, but because he's so much faster than the RAM can't keep up. So to get around that, what we do, let's pretend to open up a CPU in here. So we'll show our little guys. So what'll happen is we will put a little piece of extremely fast memory. So what we're going to have to put inside of our CPU is a little tiny bit of RAM. Now, on today's systems, we have gigabytes of RAM, but in this case, we're just talking about a few megabytes at most. But this isn't even regular RAM. We call this SRAM. SRAM is much faster RAM than the regular RAM that we snap into our systems. The problem with SRAM is that it's wildly expensive, and while we can't use it for our regular RAM, it works great for this. So what's going to happen is the prefetch part of our CPU, he is going to be watching the code as it comes in. And say there's a piece of code that says, go to a particular place in memory and grab that piece and then put it in. Well, he doesn't have that ready to go. So what he'll do is he'll start grabbing lines of code and start dropping it into the cache. The idea is that he may not even use all these lines of code, but in case somebody does call for it, he'll be ready to go and he can use it. Every CPU today has some amount of cache built into it. The problem is that if you really want to get two CPU engineers into a big fist fight, what you want to do is tell them the proper way to configure your RAM architecture is, and then shut the door real quick, because probably one of the biggest differences between Intel versus AMD is how they design the cache to be able to be ready for anything the CPU might ask for. If the piece of code that the CPU needs isn't there when it needs it, we get what's known as a pipeline stall. And when that happens, the entire pipeline is shut down, and then we use a few hundred clicks of the clock to go out and get a line of code off of RAM and get it in there, and it's something we want to avoid at all costs. So to avoid pipeline stalls, there are very big mathematical ways to do it. What's important for us to understand is that every CPU comes with cache. In fact, it doesn't come with one cache, it comes with three. The first cache, well, it depends on the CPU. There's some variance here, but the vast majority of CPUs come with three caches. The first cache is known as the level 1 cache. On almost all systems, that's about only 64K of RAM. However, this cache is so fast that it runs at the multiplied speed of the CPU. So the level 1 runs at the same speed as if it's a 3 gigahertz CPU, that level 1 cache runs at that speed. It'd be about 64K. The next level of cache is your level 2 cache. The level 2 cache is what feeds the level 1 cache. The level 2 cache is going to be a lot bigger, 128K, 256K, but it's going to run at maybe half of the clock multiplied speed. There's a lot of variance in there, so I'm not going to lock it into one particular speed. Then there's even another level of cache. almost all CPUs today have what's known as an L3 cache. The L3 cache is big. It's going to be in the megabyte size. The L3 cache is going to be running at about the base motherboard speed. It doesn't run that fast, but it runs a lot faster than the RAM itself, and as a result, it allows us to avoid these types of stalls. You can actually see the cache on your system using the CPU-Z program from CPU-ID. I've got an example of it running right here. So here we've got CPU-Z running again, and on this particular system, if you take a look, it actually shows all of the caches here. So we have an L1 cache. It's actually two separate caches of 32 kilobytes, 64K. Then we have a level 2 cache of 256 kilobytes. And then we have a level 3 cache of 6 megabytes. The 8-way, the 8-way, the 4-way, and the 12-way. That has to do with something called set association. And it actually defines how the different types of caches are efficient at being able to hand the right piece of code up to the CPU itself. It's well outside the scope of the A+ examination. However, it's absolutely fascinating. If you get a chance, YouTube has some wonderful videos that describe this in gritty detail. The nice part about caching, more than anything else, is that we don't mess with it. We buy our CPUs, and the folks who make them advertise a different type of caching. For example, AMD, when it comes to their microarchitecture of their CPUs, they believe in really big caches. Intel, they like to use really small caches that are really smart. So there's big arguments back and forth, and who's right or wrong, that's really, every time a new CPU comes out, we're always looking at the specifications and the results in terms of their performance, and it's just one of the joyous things about being a nerd is trying to determine which CPU is better based on cache. And the answer is, it's really up to you.